Variational Autoencoders, or VAEs, represent one of the most significant advances in generative AI. Let's explore how they work and why they're so powerful. In 2013, Diederik Kingma and Max Welling published their groundbreaking paper titled Auto-encoding Variational Bayes. This work introduced VAEs and fundamentally changed how we approach generative modeling in machine learning. At its core, a VAE consists of three key components. First, an encoder that compresses input data into a special compressed form. Second, a latent space where this compressed representation lives. And finally, a decoder that can reconstruct data from this compressed form. What makes VAEs special is how they handle this compression. Unlike traditional autoencoders, VAEs don't just compress data into fixed points. Instead, they learn to represent data as probability distributions in the latent space. This latent space has three crucial properties. It's continuous, allowing smooth transitions between different data points. It's compressed, capturing the essential features of our data efficiently. And most importantly, it's meaningful. Similar data points end up close to each other in this space. This architecture enables VAEs to not just compress and reconstruct data, but also generate entirely new, realistic examples by sampling from the latent space. For text generation, this means we can create new, coherent sentences by navigating this learned space. Understanding VAEs is crucial because they form the foundation for many modern text generation systems, allowing us to work with text in vector form while maintaining semantic relationships between different pieces of content. Let's look at how text is converted into numerical form. We start by defining a series of sentences such as Utica University offers courses in machine learning and AI. Each sentence in our dataset is transformed into a sequence of numbers through a process called tokenization. These numbers are then padded to ensure uniform length, creating the matrices you see here. This standardization is crucial for our neural network to process the text effectively. The tokenizer shown here is labeling each unique word with a representative number. If the tokenizer has seen the word before, it gets the same numeric representation as it had the first time. Not all tokenizers work the same way, though. Some will create a numeric array to represent each word, or they might split the word into its subword components. Some even extract the root origin of a word. In any case, in the end we end up with a series of numeric tokens that represent the source text. Because we chose to split our input body of text up by sentences and then individual words, we will need to pad some sentences to make sure that the resulting matrices is uniform. We do this by adding zeros to the ends of the shorter numeric sequences to get this resulting matrix. Now that our text is tokenized and our matrix has been constructed, we can start the autoencoding process. Here we see the architecture of our autoencoder. The input text flows through an embedding layer, which converts our tokens into dense vectors. These dense vectors are then passed through an LSTM encoder, or long short-term memory encoder. These are special encoders used when data is temporal or sequenced in some way. Our data has sentences with specific structured order, which the LSTM encoders can handle well. The LSTM encoder compresses the information into a compact latent space representation. The decoder then works to reconstruct the original input from this compressed form. The resulting latent space is nothing more than a lower dimensional representation of our source data. Because the latent space represents key features of our source data, but not the actual source data itself. We have organized the space through a training process. As the model trains over multiple rounds, we can see how similar texts naturally cluster together in the latent space. To be clear though, the latent space is not storing the text itself. It's storing the vectors, which represent key features of the text. You can see how related terms like Utica and university gravitate toward one region, while in a larger input, text situation, different topics would form their own clusters. This organization isn't explicitly programmed. It emerges as the model learns to encode semantic relationships spatially. Since our latent space is now built and our encoder and decoder have been trained, we can generate new text from it. To do this, we start by sampling some points from this learned latent space. Now we could do this in a more structured way by searching for specific topics. But in this example, we will stick with random sampling. Each point contains compressed information about text structure and meaning. When we pass these points through the decoder, it reconstructs them into coherent text sequences. By interpolating between points, we can even generate text that smoothly transitions between different concepts. One of the most powerful aspects of this approach is its efficiency. Notice how the latent space grows logarithmically, not linearly, as we add more data. Even as our input data doubles or triples, the latent space maintains its compact representation while preserving the essential relationships between texts. This efficiency is what makes these models so practical for large-scale applications. This isn't the end, however. There are various ways to continue making the latent space smaller, currently the most popular of which is dimensional reduction, also known as trimming. Thanks for watching. If you're wondering about my voice, it was cloned, and this audio was generated using a VQ-VAE model. The animations were done using a Python library called Manim. I hope you enjoyed the video.